Okay, everyone. Last video. Bittersweet. But in this video, we're going to talk about Stokes's theorem. Right? And like the divergence theorem, the main idea behind Stokes' theorem is that it's a way for us to take Green's theorem and expand it to functions involving three variables and to deal with surfaces rather than lines. Right? So to start off with, I'm going to go into another vector form of Green's theorem. All right, so for this version, let's say that basically we can write any two-dimensional vector. So if I have a vector field in 2 dimensions, even if there are three variables, because we are going to extend this to that, I know that I can always write a two-dimensional vector field like so. Plus 0k. What makes it two-dimensional is the fact that there is no k component. Um, yeah, that's all I'm going to say for now. So we know that we can always write out a two-dimensional vector field like this. We also know that we can use Green's theorem to rewrite integrals like this. All right. So before, when we talked about the divergence theorem, we looked at a different iteration of this involving a normal vector n and the arc length parameter s. All right, basically with Green's theorem, we know that we can turn this into a two-dimensional, or basically a double integral over the region that's enclosed by C. And by definition for Green's theorem, C is a Jordan curve, meaning that it's simply closed or simply connected, and we're moving along the path in a counterclockwise motion. So remember, Green's theorem gives us a way to rewrite this as a double integral. Before I get into that, right, I'm going to take a little bit of a detour. So with the divergence theorem, we were able to actually use the divergence of a vector field to rewrite a surface integral as a triple integral. Right? With Stokes's theorem, it's kind of a similar story, except we're not looking at a surface integral to begin with. Okay, we're still looking at a line integral. We're still going around around a certain path, but that path is now just the edge of a three-dimensional solid. To go into the next thing, Stokes's theorem involves the curl of the vector field F. So the divergence theorem, we looked at the divergence. With Stokes's theorem, we're looking at the curl. So if you remember, the curl is the cross product. Curl, cross, they both start with the letter C of differential operator del cross the vector field F. And if you remember the curl, we could set up as a 3x3 determinant where the top row is our three unit vectors I, j, and k. The middle row are the differential operators, partial with respect to x, partial with respect to y, and partial with respect to z. And then our third row is going to be the components of our vector field. So here we have the function m, we have the function n, and there is no k component because we're looking at a plane vector. So that would be 0. Now, when I go and actually expand this out, remember you have I times the determinant of this 2x2, partial with respect to y, n partial with respect to z, 0. Minus j times the determinant of this 2x2, partial with respect to x, m, partial with respect to z, 0. And finally, the k component, so k, the unit vector multiplied by 2x2 determinant, partial with respect to x, m, partial with respect to y, n, And then when I take these 2 by 2 determinants, partial with respect to y of 0 is, you guessed it, 0. Partial with respect to z of n, if we look back up here, remember n can be a function of x, y, and z. So we would essentially get the partial of n with respect to z as the I component. Now for the j, partial with respect to x of 0, that's 0. This will give me minus partial with respect to m, or partial of m with respect to z, I should say, j. And then for our k component, we have partial of n with respect to x, partial of n with minus partial of m with respect to y. Which is very, very interesting. Because if you've done the homework for the section on Green's theorem, you'll recognize this immediately, right? This, remember, was the integrand for the double integral that we would convert our line integrals into. Interesting stuff. Because here's the thing, Green's theorem basically tells me that I can take this line integral and convert it to a double integral over the region enclosed by C of partial of m with respect to, or not m, n with respect to x minus partial of m with respect to y dA. So basically, if I were able to isolate the k component of the curl, I end up getting Green's theorem. And here's an interesting way for me to do that. If I take this curl of f that I just computed, and I do the dot product of that curl with the unit vector k, what's going to happen? I'd multiply this by 0, I'd multiply this by 0, and I would multiply this by 1, which essentially gives me the k component of the curl. So whenever we convert this line integral into a double integral, the integrand that we get is actually just the dot product between the curl of f and the unit vector k. So we get that the line integral about the simply connected path C of f dr, or f dot dr, Franklin dot Delano Roosevelt, interesting, is equal to the double integral over the region enclosed by C of the dot product between the curl of f and the unit vector k. Oh my God, the pen died on me. The unit vector k dA. Okay, now this is going to, of course, expand into our three-dimensional space. So some things to note here. If I'm dealing with a path and a region R that's in the xy plane, what do you know about the vector k? It is always normal to that region and always normal to the path C, right? So if we take that into account, we can actually generalize this to three-dimensional space, right? Which is precisely the point of Stokes' theorem. It's to take our Green's theorem knowledge and use it to do cool, fun things with surfaces. The Stokes theorem. Yep. So Stokes theorem basically says that you can take this path integral, Franklin dot Delano Roosevelt, and you can convert this into a surface integral, right? So not just a double integral not just a double integral like we did with Green's theorem, because now we're in more than one dimension. Other thing to note here is that C actually represents the edge, like n edge of the three-dimensional solid that is enclosed by the surface S. So we can essentially convert this to a surface integral over some surface S of the curl of F dot the normal vector, where n is the normal vector that is perpendicular to the surface at a point, ds. So kind of to summarize these three major theorems, but pretty important. You might want to write this down actually. Green's theorem allows you to take a line integral where your line is a two-dimensional curve in a plane and rewrite it as a double integral over a plane region R, right? So it basically allows you to turn line integrals into area problems. The divergence theorem allows you to, with the help of one of the vector forms of Green's theorem, it allows you to rewrite a line integral, or not a line integral, a surface integral, okay, as a triple integral over the space enclosed by a surface. So it's kind of like Green's theorem if you're literally dealing with the three-dimensional analogs, right? Instead of a line enclosing an area, you have a surface wrapping around a solid, right? So divergence theorem, you can rewrite the surface integral as a triple integral where your integrand is the divergence, which is in the name, divergence theorem. Right, so Green's, you go from line integral to area, okay? Divergence, you go from surface integral to volume. And Stokes, you go from line integral to surface integral, right? That's different from Green's theorem because in Green's theorem, we were looking at a plane region, right? Stokes theorem, we're actually looking at a surface itself, okay? And just remember, divergence is part of the divergence theorem. Curl is part of Stokes theorem. Divergence dot product, they both start with D. Curl cross product, they both start with F. Don't confuse that here though, because all of these integrals involve a dot product. That mnemonic is really just so you remember how to calculate divergence and curl. All right, but anyway, this is Stokes theorem. This is it. This is the whole bread and butter of this last little piece of your Cal 3 course. So let's look at an example or two, and then we can wrap this up and get through, take your fourth exam, take your final, and get on with the rest of your summer. Okay. So for our first example, let's say that we have a path C. And this is going to be similar to the example that we looked at for the divergence theorem, where we have basically a plane, but we're only looking in the first quadrant or first octant. Right. The difference is, remember, C is a line, it's a path, it's just a space curve, not a plane curve. So C would literally just be the pathway going around this triangle, right? And S is the three-dimensional surface that's enclosed by that pathway. So it's kind of like Green's theorem, but you can orient the region any way you want, right? And bend it and yeah. All right, so anyway, C is described as the path going around in this triangular motion that is a part of the same plane that we looked at with the problem in the divergence theorem video. All right, so this surface S is a part of this plane. All right, we want to evaluate, or we're also told that our vector field F is equal to negative y squared I plus zj plus xk. So we've got our path, we've got our vector field. The goal for this problem is that we want to evaluate this line integral about the path C of f dot dr. All right. And if you remember f dot dr, that should look also pretty familiar because remember when we did our yeah, because remember when we did our video on surface integrals and we talked about flux and how to calculate flux, this was the integrand, right? The only difference is that we were doing a surface integral of this, right? So anyway, we want to evaluate that integral. So the actual work for this one. We already know because of Stokes' theorem that we can convert this line integral about this space curve path into a surface integral. And the reason that we might want to do that for this one, right, is because if you look at this path, if I were to try to evaluate my path integral as a path integral, I would actually need to split this into three separate pathways, right? You have the leg of it that goes this way, the leg of it that goes that way, the leg of it that goes that way. So you would have to do C1, C2, C3, figure out all three line integrals and then add them together, right? But with Stokes' theorem, we know that we can actually evaluate this entire thing by just doing a single surface integral because we only have a single surface enclosed by that path. So with Stokes' theorem, I know that I can rewrite the path integral of Franklin.Delano Roosevelt as the double integral over the surface S, which again is enclosed by this pathway, of the dot product between the curl of F and a vector that is normal to the surface at a point, which because this is a plane region, n would actually be orthogonal to the surface at any point because it's flat. Right, but this is a general thing that can also be done pointwise for surfaces that are not flat. And we're doing this with respect to the surface S. Okay. So first thing we need to do is go through and determine the curl of F. Remember, we can do that by taking the cross product, right? Curl cross product of the differential operator del with our vector field F. So setting up my determinant, first row is my unit vectors. Second row are my differential operators. So partial with respect to X, then with respect to Y, then with respect to Z, right? And then my last row are the components of the vector field F. So negative y squared is my I component, z is my j component, and x is my k component. Now I can write out my 2x2 matrices. So remember, you cover up first row, first column, you get d dy, z, d dz, x, minus j. Never forget that minus, it will trip you up if you do. Right, we cover first row, second column. We're left behind with d dx, negative y squared, d dz, x. And lastly, k. If I cover up the third column, first row, I'm left with d dx, negative y squared, d dy, z. Okay. Now if I go and compute these determinants, we have d dy of just x, that's going to be 0. Minus, and then derivative of z with respect to z, that's going to be 1. So my I component will be negative 1. For j, derivative of x with respect to x is 1. So minus, and then 1. Subtract from that, derivative of y squared with respect to z, that would be 0. And lastly, derivative of z with respect to x is 0. derivative of negative y squared with respect to y is minus 2y. So minus a negative, we add 2y. So altogether, my curl is going to be the vector negative I minus j plus 2yk. That's the curl. So now that I know the curl, I just need to figure out what my normal vector is. And if we were to look at, say, the outward normal vector, right? So think popping out of the surface at a 90-degree angle to the surface. We can actually get our normal vector n in the same way that we did for flux integrals. So n, that normal vector, is going to be equal to, we have negative gx for the I component, and we have negative gy as the j component, and positive 1 is the k component. All right. So to remind you, what are these g's? When we were doing the flux integrals and surface integrals, remember we had to isolate z, right, from the surface. And then whatever z was equal to, that was defined as g, right? So if I take the surface that we started with, which to remind you was 2x plus 2y plus z equals 6, we can rearrange this to isolate z and get z equals 6 minus 2x minus 2y. All right. So if I take the partial derivative of this with respect to x, I end up leaving behind just negative 2. So negative 2, so negative 2i. All right, and then for g, that should also be negative. All right, derivative with respect to y, we get negative 2 again. So negative 2, and we don't have any work to do for k. So altogether, we get 2i plus 2j plus k as the normal vector n. So to go back to, so to go back to this surface integral that we're doing, we can write the surface integral out as an iterated integral, right? And if I actually write out my curl in component form, we get negative 1, 2y. If I write my normal vector in component form, we have 2, 2, 1. All right. So then my integrand, we're going to get negative 2 plus negative 2, so negative 4 plus 2y. So altogether, 2y minus 4 ds. Okay, so we can at this point go ahead and write this out like we would just a typical surface integral. So with respect to y, then with respect to x, or we could do with respect to x, then with respect to y. It all depends on what is easier and what's easier for us to see when we look at this part. So reminding you, to set up the bounds for this, we need to look at the xy plane. We know that in the xy plane, we have this part of the path c, right? And remember, by setting z equal to 0, we get that this line is 2x plus 2y equals 6. If I divide everything by 2, we get x plus y is equal to 3. And remember, I can either solve for x in terms of y or y in terms of x. It doesn't matter, but it will affect how I can set up the differentials. So if I go the other way than what I did in the divergence theorem video and solve for x in terms of y, I get that x is equal to 3 minus y. And we know that because we're in the first octant only, the y would have to be 3 or smaller as well. So that said, I know that my inner integrand will go from 0 to 3 minus y. Integrand was 2y minus 4. Since that has a y in it, my differential has to be dx. And then my y values, like I mentioned before, have to be 3 or smaller, right? But not below 0 because then we wouldn't be in the first octant. So now that I've set this double integral up, I can evaluate that one actually really easily. So we get the integral from 0 to 3 of x times 2y minus 4 evaluated from x equals 0 to x equals 3 minus y. Then integrate with respect to y. So if I multiply that out, right, because I know plugging in 0 is going to give me 0, but if I plug 3 minus y in, then I can double distribute to figure out what this works out to. I know we're going to end up with negative 2y squared, right? And then cross terms, we get plus 6y and plus 4y, so plus 10y. And then constant term, 3 times negative 4, we get negative 12 dy. All right. And then at that point, we just do the really simple Cal-1 integral that I'm not going to spend time doing because it's kind of super simple. We end up getting negative 9 as the numerical value. So we were able to figure out the value of that line integral without having to split into multiple pathways. Instead, we could just use the surface that is enclosed by that pathway, by that set of pathways. All right, so now that we've done that, let's see, they did have, I do want to talk a little bit about the physical interpretation of what curl actually is. So if you remember, divergence kind of related back to flux. Flux, remember, being the rate at which things pass through a surface. Divergence, remember, was how easy it is for something to pass through a surface. In a similar way, we can think of curl as how likely it is for a force to curl around a certain point. I like to think of it as like cowlicks. I mean, yeah, I know I don't have any hair, I can't relate, but like anyone who has a cowlick, like say here, would notice that the hair actually grows in a circular fashion around that cowlick. So we would say that a cowlick is a point on your scalp that actually has a high amount of curl, right? Because the hair that grows there is very likely to wrap around that one point on your scalp. Whereas something out here where maybe you don't have, this is just comical, me talking about hair. All right, but if you have a patch of hair here that grows relatively normally, right, not around a certain point, then you would say that that area of your scalp has very little curl, right? And this, and you can even think about it in terms of curly hair, right? Like if I have super straight hair, there's no curl around a certain point, the hair is just growing straight out. But if I have hair that's really curly, right, you notice that it kind of wraps around sort of the Z axis coming out of your head, right? The vector normal to your skull. So that's another way to think about it too. All right, so curl is just the tendency of a vector field, which can be your hair, which can be the wind. Like if you've ever looked at the weather forecast during a hurricane, you know how it makes the eye of the hurricane. That's because the wind, the barometric pressure, all of these things have a high amount of curl about the point that makes the eye of the hurricane. So there are a lot of ways that you can kind of physically think about ways that curl manifests itself in the real world. If you're looking at fluid mechanics, that's also another thing. Thinking about maybe water that goes down a drain, right? There's a higher amount of curl the closer you get to the drain. So with that said, Yeah. Yeah, with that said, let's do one more example for fun. Okay. So in this example, we're going to look at something that's actually a fluid mechanics application of this. So let's say that we have some kind of a cylindrical container, right? And inside this container, you have fluid that's going around and around and around, right? Think of it like you're making a pitcher of Kool-Aid and you're stirring the sugar in, right? Let's say that F in this case represents the velocity field, so the velocity of the fluid, all right? And we'll say that F is given to us by this vector field. We have negative y square root of x squared plus y squared I plus x times the square root of x squared plus y squared j. All right, and we want to find the surface integral of the curl of f dot n ds. Right, where S is the upper surface of the cylindrical container. So S is upper surface. Some other things that we're told about the cylindrical container are that the radius of the container is 2. Yeah. So, okay, so S is the upper surface of the cylindrical container, meaning that, yeah, meaning that the path C that we would take around the equivalent line integral would just be the circular rim of that cylindrical container. Right? Either way, you get the equation of a circle as your surface. So with that said, first thing we need to do is figure out the curl. So the curl of F, we'll set up our 3 by 3 determinant. Right, and we get negative y square root x squared plus y squared, x square root of x squared plus y squared. And then there is no k component, so 0 for that one. And this will turn out to be relatively simple because of how these guys look, at least for some of these. So for I, right, if you cover up that first column, first row, derivative of 0 is 0. Derivative of x times the square root of x squared plus y squared with respect to z is 0. There's no z in there. So the I component will be 0. We do not have an I component. Minus j. Now, if I cover up the second column and the first row, I'm left with that 2 by 2 determinant. Derivative of 0 is 0. Derivative of this with respect to z is also 0 because there's not a z in there. So there's also no j component either. And lastly, if we look at the k part, all right, we're going to get the partial with respect to x of this guy minus the partial with respect to y of the other guy. All right. Wow. All right. So at this point, Yeah, so at this point, I know that I can take this negative out, make that a plus. I know that my curl is going to end up being the sum of these two partial derivatives. So looking at this one, remember we can write x times this square root part like so. So that if I take the partial with respect to x of all this, I end up getting a product rule with chain rule. So derivative of x would be 1. So we get the square root of x squared plus y squared plus x times the derivative of this should be 1/2 x squared plus y squared to the minus 1/2 multiplied by the derivative of the inside with respect to x. Okay, so the 1/2 times the 2 will leave us with 1 times x. And rewriting that, I end up getting the square root of x squared plus y squared plus x over the square root of x squared plus y squared. And I know that if I take the partial derivative with respect to y of something that looks very, very similar, the differentiation is going to work out relatively similar. So derivative of y is 1 times this original. All right, plus then we're going to end up with pretty much the same thing, except with the y on top. Okay. So then when I add these together, and so take the sum of these, I end up getting 2 square root x squared plus y squared. Remember, that's what I would get from just combining these two, plus x plus y over the square root of x squared plus y squared. Oh, yeah, forgetting a squared here. That makes it easier. All right. So, one thing to note here is that this is basically that square root if I were to square it. So what ends up happening is that this whole term simplifies to just the square root of x squared plus y squared, which I can then combine with this. So I get 3 times the square root of x squared plus y squared, and that is my curl. So now I've figured out the curl. Next thing I need to do is figure out my normal vector. But actually turns out to be pretty simple, right? Because this is a circle, like if you look back at our surface, it's a circle that is parallel to the xy plane. What vector is perpendicular to the xy plane? It's k. It's gonna be k. All right, so my curl ends up being this vector 3 square root x squared plus y squared k, which means that my integrand for the surface integral I have to find is going to be the dot product between my curl and the vector k, which ends up literally just being 3 square root of x squared plus y squared. Yep, because I'm multiplying that times 1. So I get that. Which means that the surface integral that we're doing can also be written like that. Now, this is where we can convert to polar coordinates, which is something that you may have been screaming at me from the point where we saw what F was, right? Because that's got R's in it, definitely. So when we go to set up our surface integral, we're going to use polar coordinates. So if you remember, the radius of that circle was 2. So 0 to 2 will be my R. And then since we're going all the way around the circle, theta is going to go from 0 to 2 pi. The integrand turns into literally just R, and then ds, remember, is going to be R, is going to be a R dr d theta. So if I multiply R times R, I get R squared. Now, if I take the integral of that, I end up getting R to the third over 3, which will evaluate from R equals 0 to 2. Notice that we can also pull the over 3 out front and make it so that these are basically just 1. So now if I plug 2 in, I get 8. If I plug 0 in, I get 0. So we're really just taking the integral from 0 to 2 pi of 8 d theta, which gives me my answer, 16 pi. And there we go. One last side note, because we did talk about curl again, is to remember conservative vector fields. And honestly, if you remember that, you may have noticed that the ways that we check for conservatism in vector fields corresponds to the integrands that we get in Green's theorem and kind of ends up coming into Stokes theorem and the divergence theorem as well. Right? So in general, remember, if you have a three-dimensional vector field that is conservative, what's the way that you test and how do you know that it's conservative? You have to look at the curl of that vector field. If there's no curl, that's a kitty in a box. All right, if there's no curl, then remember that means that the three-dimensional vector field is conservative. And if that's true, what would be true about the surface integral? It would be 0. Yep. So that's another thing to keep in mind. All of this kind of connects back together, right? Vector fields, conservative or not, we look at the difference in partials, kind of like what we look at in Green's theorem. We look at the curl for three dimensionals, which is used in Stokes theorem, right? But really, that's a very interesting thing that you hopefully have been able to recognize at this point. And if not, it just means that you need to do more math. And with that, I bid you adieu. Have a great rest of your summer. Good luck on your exams and happy mathing.